इसको है ना थोड़ा जल्दी कवर करेंगे. देयर आर कुछ टॉपिक्स है जिनमें थोड़ा सा टाइम लगेगा, तो छोटे टॉपिक्स के definition करके and then I'll provide those notes as well. But primarily what we will like be stuck with today is data normalization and VC dimensions. Okay, तो start कर देते हैं. First of all, like basic सी definition दे देते हैं machine learning की. Primarily when you are trying to let's say 1 second. So primarily when you're trying to train some kind of machine to make a decision for you is when it is like machine learning. So machine makes decision. That is what machine learning is. I mean that's an apple. I mean that's a what's it called? A result of machine learning. Sorry, learning. So there are so many different ways to actually go around, go about training machines to make decisions. Like there are just, you can simply go ahead and write an algorithm to just create, you just make a linear decision, either left or right, true or false, yes or no, that kind of thing. But then there are also certain different complex problems where you might have to take multiple roads down a path and decide accordingly, like which path you had to take. And one of these decisions might have been right, the other might have been wrong, some might have been partially right. So for these kind of things, you can a lot of times write algorithms if the decision tree isn't too big. But most of the times decision trees like grow exponentially, so it's kind of hard to do, hard to write an algorithm if it's going to be like more than 5 or 6 levels of that many times you have to make a decision. So for those kind of things, what you do is you start using the actual machine learning or the deep learning algorithms. So for those, you have things like perceptrons, which is just one single neuron, which also gives you the neural networks. You also have other classifiers. So classifiers. So good example of that is what's it called? Random forest. So that there is also some problem which are very linear, even though they have a lot of decisions to be made, and they can be solved with regression as well. So regressions, there are like at least 50 different regressors. So you can like, I guess I could just name two of them for you, like easy ones: linear regressor, and then there's random forest regressor as well. There's also like, other than linear, there's also like a little bit of higher order regression you can make with splines. Anyway, so these are like these are different things you can do to create decisions, and like you can program them in a certain manner where it can automatically take decisions at certain points. So yeah, this is what machine learning is in basic definition of that. Okay, so now the other part is like, this is just a definition of machine learning. This part. Let me mark that one. Okay. Now let's quickly talk about certain terms that we will like run into a lot in this subject. So, for example, what is a model? A model is basically it's a mathematical representation of an algorithm. Let's just put it this way: this is the machine that machines code that makes decision. That's what a model is. Like, it creates a decision based on how you want it to take the decision. That's what it is. And there is training. These are all like technical terms that you will like run into like throughout the subject. Whenever you use data to actually train, I mean, whenever we use data to set parameters. So parameters of these models, parameters of a model, it is called training. Then after training, there is testing. It's basically just telling how good or bad a model is. It's a metric to tell if the model is good or bad. By the way, I'll be sending these writings kind of a little bit bad. Sorry about that. But yeah, I hope it is like slightly understandable. Um, After testing, there is also features that you need to understand. This exists in data. So feature is basically anything, any specific thing which you want to take as an input or give as an output. So think of like two-dimensional data where you have two columns, one of which you can think of as an input and one of which you can think of it as an output. So these are both features in that case. Although the output one is like just there, kind of like acts like a label. I'll also talk about label actually. So first of all, usually input, usually used as input, feature used as input. It is part of the data. All right. Then there is labels. So a kind of feature which shows the final result that we want. That is what a label is. So think of it as expected outcome, or or what else can we call this?
Target.
Target. Yes, target. Yes, that is a perfect word. Then there is overfitting and underfitting. Let's quickly talk about those. Overfitting. So what happens is whenever you train a model, sometimes when you are training on a very small amount of data, you might think that I could reuse this data to kind of keep on training the model over and over again. But what that does is it trains the model very specifically just for that limited amount of data, which means whenever it sees unknown data, it can usually never handle it, and that is what overfitting is. So too much. Focus on small data.
We can say training data set.
Yeah, training data set. Small training. I'll just write training. Oh my god, let me write. There we go. Training. There we go. Yeah. So this leads to what exactly? This leads to the model failing. Model fails at new data. That is overfitting. Now the underfitting is like the other way around. Underfitting. So what happens here is like the data is not like, even though there's, you might have, okay, so I'll just write it, might have big data, might have big data, but either model is not sensitive. So I'll write this, but model is not sensitive to that data. Model is not sensitive, or the data uh, is just insufficient, is insufficient. Yeah. So in this case, what happens is like it just can't find a pattern at all in whatever amount of data you have, which means it will just not work on the actual, but it will just fail. Like the model will fail.
So we can say, right, that overfitting is a condition where our like model is too much dependent on the training data set only, that it
Yeah.
gives highest accuracy for training but fails for this test
The,
data.
yeah, the other data, test data, just it fails
Yes,
on test
correct.
data.
And in
And
underfitting, it does not give better result for training as well as the test data.
In underfitting, actually, primarily what happens is like either the data where you wanted to find pattern, that data is insufficient, or the amount total overall amount of data is insufficient, or something like that, which led it to not train properly, or maybe there is just no correlation. That, but that is a
So,
different thing. Yeah.
like all models trained on very small data set will lie into underfitting condition. Is it true?
Not all, by the way. There are very specific small data, I mean, small models. For example, if you were creating a model for, like, say, logical gates or circuits, in that case, small data set is perfectly fine for that. But
Okay.
those are linearly solvable problems, which means that you do not really want to use machine learning for those. So, yeah. It's like those exists, yeah, those exists, but it's just that you don't want to do machine learning on them either way. Made sense?
Yeah, yeah,
Okay,
completely.
okay. So now let's talk about hyperparameters. Hyperparameters are just, let's see, hyperparameters. Okay. So think of, like, when we have a model might be like, making decision like this, um, on like different ends, like, it reaches this fork and then this fork, it ends up around here. So it makes a decision to go there. Now what happens is you kind of figure that, okay, this is like the right path for decision, except that I wanted to go into this direction for this one, and I wanted to end up here. So what you do is, instead of like directly editing the model, you do not edit like these decision making algorithms here, not this one, but what you edit is a small parameter that you have added somewhere around the line over here. So this might have a parameter here, over here, over here, over here, over here, over here, and you might be able to adjust those directly. So these are what hyperparameters are. So making small adjustments that you actually have control over, those are the hyperparameters. Now, a good example of this is definitely not bias, by the way. So weights, BIGSTS, and bias are not a good example. The reason being that those are not in direct control. So because no direct control.
So, like Ashutosh, like
Yeah.
hyperparameters, what are we changing? Like these dots that you created, what are they?
So think of, okay. I'll tell you what. The weirdest thing will happen when you kind of create the ANN and stuff. Sometimes the model will train on the same, like, data is the same. So let's talk about this shortly. Data is the same, and you train it twice on that model. You choose the same model, so model is the same, and this is like model 1 that you have trained, and this is model 2 that you have trained. And you will find out that more often than not, when like you haven't really trained it for like a million times or a billion times, these models will differ by a lot. So for example, this might have an accuracy of 60% and this might have an accuracy of 97%. And the reason that happens is because of the starting parameters. So things that you have in your control, for example, the initialization uh, of what, like, weights and biases, initialization of that is in your control. That becomes a hyperparameter for the first time, that's it. But after that it doesn't, because it gets adjusted automatically. The other thing that you have in hyperparameters are how many times you're training. So that is called epochs. The other thing would be how big the data is, batch size of the data. Size. There is also learning rate, by the way. So learning rate. So these things come under hyperparameter. Now the reason they come under hyperparameter, even like initialization of weights and bias comes under hyperparameter, is because at this point, these things are like initialized by you. These things are created. I mean, you write these things and you make a decision. And the reason these are different from here and here is because between whatever amount of epochs and the data you have used, sometimes you have a gradient descent happening in like most of these models. And in this gradient descent, it might find a local minima somewhere, different in this model and somewhere different in this model. So maybe it will find it over here, a local minima, and it might find the local minima over here instead on the model one. So these models are like very different from each other, even though they have been trained on the same data, even though they've been trained the same amount of times. So what you do is to remove all of these inconsistencies, you increase something like, say, you increase the epoch by 1 million, or you increase the size of batch size, you decrease the batch size of the data if you're doing image processing. If it is like numerical data, then you can obviously increase the batch sizes. You try to increase or decrease the learning rate to see like if it kind of converges faster. You also, change the initialization conditions. So for example, in one of the classes we did this, where we were using uniform distribution, and we started from -1 to 1. So everything, weights and biases, were between -1 and 1. But it didn't train the model properly, and then we switched it to -0.5 to 0.5, and it started training the model perfectly fine. So these are hyperparameters, like the things, initial conditions that you use to train your data. I mean, train your model. Does that make sense?
Yes, yes. So basically, we are tuning it, okay, as per.
Yeah, yeah, yeah,
Okay.
yeah, yeah. Just remember, hyperparameter is just something that is in your control very explicitly. And if it isn't in your control, then it is not a hyperparameter. It is then there's just a parameter of a model.
Okay.
Mhm. Okay. So
So,
next up we have.
so basically, like
Mhm.
we can say na ki these are the variables that are
Mhm.
manually set before training a model.
Yeah, yeah. Before training the model, these are the hyperparameters.
Got it.
Yeah.
Take
Yeah.
take
Hmm. Okay, so next up, algorithm. Let's quickly talk about algorithm. Not sure if I really need to define this, but it's just a step-by-step procedure that you follow to solve a problem. Uh, so for ML, all it refers to is like different types of methodologies that you could use to solve the same decision-making problem. Like literally, that's it. After this, we will we have a few more. Like for example, training set. So let's talk about set. So whenever you have a data set, what happens is like you have to divide it into two different parts. The first part is going to be training. The other part is going to be testing. Usually this is 80%. This is 20%, and that's just how it is like in most of the frameworks. So you don't have to worry too much about it. Um, so yeah, that is a set. That is a set, just a set. And then these things are called training set, and that's a testing set. That's about it. Now you have like labeled and unlabeled data. So we talked about labels like earlier. Then there is labeled and unlabeled data, the same kind of thing. Labeled and unlabeled. It's like I'm going through the definitions. Okay, so a labeled data set is useful for supervised learning because usually what the model will do is it will do some kind of processing, give some kind of output, and then it wants to check. So it wants to check if the output is right or wrong. So if it is right or wrong, and for that you need the label data. So it checks from the labeling. And unlabeled data is used for unsupervised learning, where the machine takes some input, tries to find some kind of pattern in that data, but it doesn't know what it is trying to find. So if it finds a pattern, well and good. And then after like finding the pattern, you can actually label it afterwards. Like you cannot do it like before it actually finds that. So yeah, that's like unlabeled data. Like it's not telling the computer what exactly they are looking for, or like what kind of output it should be like getting. So it cannot check if this pattern. So checking is not possible at all. Like that's just not possible if this pattern is correct or not. So that is for unsupervised. Unsupervised, and this is like supervised. Okay. Now let's talk about um, validation. Or let's also talk about, okay, so validation set and validation, let's just talk about that. Yeah. uh, Sorry, cross validation and validation set. Okay, so when it comes to cross validation, it is basically it involves, let's say, data. So say you have a lot of data, and okay, let's think about it like in a manner where we have like multiple models being trained on the same set, or you have multiple different, so this time models M1 and M2 are different. So this might be a regressor, this might be a classifier. All right. And there are certain problems, by the way, like very small problems that can be solved by both regressors and classifiers, definitely. So you could choose either one. You could choose M1 or M2 to go with it. Now, what happens is like the process of validation is just you trying to figure out if this model is better on the given data set or this model is better on the given data set. So when you test so the testing set is used as a validation set as well at times. And all you want to do is like, same data goes into, like, you divide it into two parts, this one being 80% and 20%, this one being the training, and this one being the testing set. So this one test and this is train. This goes into this, same thing goes into this for training, and then you try to validate it using this test, if this one is better or if this one is better. And that's just basically cross validation, as long as you have more than one model. And validation set is like the test set if you are like validating something. It's no different from that.
So comparing which model is like which like algorithm or algorithm is best suited for our model is known as cross validation in a nutshell.
Okay, so if you think about, if you have heard about the MNIST set, so for example, like the machine, what's it called, the vision, computer vision part, OCR and handwriting recognition and those kind of things. What you do is on those kind of models, you take a validation, you create a different validation set like this. So say this is your whole data, your training data is like right here, train, and this is the test data. There we go. And what you want to do here is like you divide it into batches, like this training data gets divided into batches, and from each of this batch you take a small amount of data. This is a different kind of validation, by the way. It only works with computer vision ones. So deep sorry, what's it called, yeah, deep neural networks. Yeah. So you take these small amounts of images from each batch, and then you try to use those to kind of validate your, if your model is being trained correctly or not. So that is the other kind of validation that you use. That is like, if I mean, we didn't get to that yet. I mean, IEST said we were going to try and do that, but we didn't do that. Usually, this is more associated with. Let's talk about batch processing as well over here. Hold on. So let's go back a little bit over here. I mean, to explain this part, by the way. So when you have a data set which is like say 500,000 big, say 500,000 images in there, and you just give the computer to process, you give this data set to the computer to process it. What it does is like it will take one image and it will just process it, go through it, and then it will try to adjust the curve of the model somewhere, and then it will take the next image and adjust the curve again, next image, and then it will adjust the curve again, and next image and adjust the curve again. This takes a long time to do. So what people do usually is they kind of take this data set and divide it into very small batches. So say 1,000 images each, and then they try and do the same process. This whole process goes, it will do these 1,000 images, and then it will kind of, validate through that. And then it will take the next 1,000 images, and then it will kind of check, if the curve is like in the correct direction or not. So it will keep on doing this, and this is part of what is called the stochastic gradient descent algorithm. So this specific algorithm requires that you take those validation sets out of these smaller batches. So this is a very specific use case scenario where it is best suited, and like you have to take it from like these small batches. So that stochastic part. So does that answer your question, by the way? Like this is the kind of machine learning which uses validation the best.
Okay, yeah, a little bit.
Okay. Ah, okay. So that's most of the things. Like let's talk about what kind of data we can work with. So like if we scroll all the way up here, we have data sets for machine learning and different paradigms of machine learning. So definitions are done. Like at this point, definitions are done. Let's quickly do the data sets for machine learning. Now, what kind of data sets do you need? Really depends on what kind of learning you are doing. Let's talk about data set. There are certain types of data sets. So for example, data could be just numbers, numerical. Data could be words, so more of a language thing. Data could be images. It could be audio. It could be audio. It could be a video, or perhaps it could be something which is not in a specific format right now, like something which we might not have thought about using machine learning on. So it could be something else as well, definitely not limited to this. Now, a data set, a good data set, let's talk about what a good data set is. First of all, data is standardized. So for example, if there are images, all the images are of the same dimensions, same dimension. Data is normalized. So for example, numbers, if they are like big, then let me give you a really good example of this. Imagine this graph where it shows your height. Say I'm gonna just write in something like 5, and then 10, and then 15. Okay, so this shows your height, right? So this just shows your height, this bar, this one. And what if I put some kind of bar right next to it which shows your salary? So this is like very disproportionate. This would be very disproportionate because your salary isn't going to be like 20-30 rupees or something, but a lakh, 2 lakh, something, 3 lakh, 4 lakh per month, something like that. So in front of your height thing, this graph, your salary thing would be like huge, right? Because this number just goes up to like 6 or 7 feet, and this number goes up to like 200,000 maybe. I don't know, depends on you, right? So you would barely be able to tell any difference if between two graphs, if this was something you were looking for in front of this compared to this. So what you do is you take this huge thing and you try to fit it in the same height, and there are like multiple ways to do that. Like there are like 10, like, no, if I say multiple, I just mean 10 different ways to do that. So those are all normalization. So something like min max, and we will do this as well. You can also do the logarithmic one. There is also z-score normalization, and there is like 7 more. We'll talk about those. So this is what like normalization is. Like all the data like kind of looks something comparable, so you can actually look at the graph and kind of tell what the difference is. So normalization also just means that most of the data lies between 0 and 1. 0 and 1. A lot of times people will take, like, even with normalization, a lot of time people will take -1 and +1. That's perfectly fine. It depends on like those people, like people and their decisions. Some people would like to take like 0 to 2, because 1.25 or something like that. They might allow that kind of number. So depends on like what kind of data you have, and depends on what kind of what's it called, like what kind of application you need from that. Makes sense so far, by the way?
Yeah, so one thing like
Yeah.
the normalization that like you are saying. So
Mhm.
normalization is basically, we can say, just like reducing the randomness between data, right? If
No, it's like not reducing the randomness between the data, but like, okay, look at this. I'll quickly do this again. Okay, imagine your height is 6 feet, right? And your salary is 120,000 per month. Will I be able to tell if your height is 6 feet or 6 feet one by looking at this? Even if there were like numbers right here, and there's like 120,000 here, will I be able to tell anything about this graph? No, not
yes, yes,
particularly, right?
yes, yes.
So what I want to do is I want to scale this part down so that these kind of look like come to a similar, thing where I can see enough details of this graph so that I can infer something from it. So after normalization, this might look something more along the lines of,
But
um,
again, if we like proportionally reduce it, that bigger
mm,
graph, bar graph, and
yeah.
we need to do it for smaller also to maintain the relationship between them.
Yeah, kind of. So if you were to reduce the smaller one, say the highest height is going to be 7 feet. So in that case, you just make it, say this is one, you make it like say 0.7 or 8 or something like that. And for salary, say highest is like 250,000. So in that case, you make it half of that, one. So now this is like more up to scale between 0 and 1. Like this would be 6 feet, but like scale down to 0.7 or something, and this would be scaled down to 0.5 or something. That is 120,000, right? So now it looks like kind of comparable, where I can see like, okay, this guy has this much height and this much salary. Does it make sense? Like, does this example
Yes,
even
yes.
make sense? Okay. Okay, good. So normalization, the good data is like normalized. That is one more thing. Where is it? There it is. Standardized, normalized, clean, like without much noise. Okay, there we go. That's pretty much the three things that you need from like a data set. Does that like the- um, there is no other thing that can make a data set better or worse than other than these things. These things will mostly, normalization, by the way, increases the processing speed. So I'll write that down as a processing speed. Okay, there we go. Clean data allows you to not worry about outliers or something weird happening in the data, where like some weird result comes out, like unexpected results. And standardized data just helps you like, um, kind of keep a standard for the data, where you can like, even if you're required to clean the data, you can do it in batch processes. And like standardization primarily helps you do the batch processing. So this helps with batch processing. So this is good data, like definition of good data basically. Now let's quickly talk about different paradigms of machine learning, and then we quickly move on to normalization. We should be able to cover that easily. So let's like paradigms. Dig paradigms. I don't know how to spell that shit. Okay, so first of all, the first thing that you need to know is supervised learning. Uh, and supervised learning is basically when you have the input, you have the output, and you just have to find some kind of either classification or regression. So regression or classification. There we go. Bad handwriting. Then there is unsupervised learning. Over here, all you want to do is find a pattern, You have the inputs, but there is no output. Like, let me scroll down a little. There is no output here. I mean, there is no output to validate your things, like check your like output kind of thing, you know. You just have to label the data, label the classification later on. After that, there is reinforcement learning. In reinforcement learning, it is primarily more of a reward and punishment thing. So, reward and punishment is part of algorithm, part of learning algorithms. Punishment, I guess I could have written penalties. Well, I'll just write penalties actually. That's the better word. Reward and penalty. Penalties. There we go. Over here, you do. I mean, it could be either one. Like, you know, you could have input and out. I mean, you do have an output data. So let's say input is there, output is there. In most cases, a good example of this might be, say, a game where you're trying to like train an AI for a game. AI for a game. Even like, you know, self-driving vehicles, robotics, or yeah, I'll just write that. Okay. Then there is semi-supervised learning. Semi-supervised learning is more of a, say, text and image. Let's just go with image recognition. Like for an example here, example image recognition. What was that model that we were working on the other day? Let me. It had a really good, yeah, YOLO 8 example of this. YOLO 8, YOLO V8. That's an example of that. And then there is also text classification. So text classification. So yeah, these are the examples for semi-supervised. And how you do that is like basically you take a lot of data, which is like some of it is labeled, some of which is not labeled, and yeah, you just process those both together. And then from the labeled data, it learns something and it tries to label the unlabeled data as well. So yeah, that's semi-supervised. Then there is self-supervised and transfer learning as well. So let's self-supervised. Over here, we just set up a target. Okay, sorry about that. So primarily in self-supervised learning, we have models. Deep learning, these are deep learning models. And what they do is they will usually like not have labels, not have labels, and they will like try to figure out what they're trying to see. Like, you know, they try to figure out what they are looking at. And this is more like, you know, what they are looking at might not be the best way to describe it, but more of a, you know, what pattern they are looking at. So pattern, because these are used for pattern recognition. And then finally there is like the transfer learning, where you solve one problem, gain some knowledge from that, apply to other problem. This is called a transfer learning. So transfer learning is more like, when you have a base model. So something like, I was talking about this, the what was that? Semi-supervised? Yeah, semi-supervised. So YOLO it, and what you do is you take this model and you train it on your own images, and then you make your own model out of it to kind of recognize. Suppose you wanted to just recognize a laptop in an image, so your model would be like, it would just recognize laptop, and like you transferred some kind of learning from an already existing model to train on your own data set, and then you got your own model out of that. So that's a example of transfer learning. So these are all the paradigms that currently are like, in machine learning. So supervised learning, unsupervised learning, reinforcement learning, semi-supervised, self-supervised, and transfer learning. These are the ones. And with that, we are like done with this first line of the syllabus. Now let's quickly talk about data normalization, because we have like say 18 minutes, and we'll like do 5 or 6 techniques of normalization. So first of all, I did explain a bit about normalization, right? When you want certain features of a data set to be like visible against each other, kind of. So you normalize them, put them like between 0 and 1, so you can kind of compare them between each other. So there are different ways to do this, all formulas, by the way. So let's talk about those. So the first technique that we are going to use is min-max normalization. So min-max normalization. There was definitely some doubt in here the last time the professor was teaching. So simple formula, whatever thing that you are trying to, what should call normalize. So say you're trying to normalize your height, say 6 feet, right? And the highest height, so the lowest height say was 5 feet, and the highest height is 7 feet. This is the lowest, this is the highest, this is the one that we want to normalize. This is what do we call this thing? A specific entry in the data, like what's it called? I completely forgot. A row in a feature. Yeah, it's just a row in a feature. So you want to normalize this. What you do is you take this 6, and then you subtract the lowest amount, this one, minus 5, upon you take the highest minus lowest. So that would be 7 minus 5, that would be 2. So 7 highest minus 5 lowest, and that gives you that is 6 minus 5 1, and by 2, and that gives you 0.5. And now this is normalized between 0 and 1. Make sense? I'll write down the formula, by the way, 1 second. So let's take feature minus lowest upon highest, HIGH, highest minus lowest, and that's just normalization, like min-max normalization. Any doubt in that one? Oh, is there reason during training? Oh my God, I haven't been looking at the messages. Sorry about that. So Anugrah asked, overfitting model was preferably valid on training data, but fails on production by test data. Yeah. Is the reason during training the model gets repeated exposure to the training data, and if the model is too complex, too many parameters can memorize a specific pattern, noise, and other. Yeah, that's true. The fails underlying the general rules and predict based on the specific patterns on the training data set which exist in the data. That's definitely true. And yes, it is being recorded. So yeah, that is the first kind of normalization. Let's go to the next kind of normalization, which is the z-score normalization. Any doubts on this one, by the way? Anyone? No one? Okay, for z-score normalization, it's more of a statistical method. The one that you want to normalize, say you have a feature. So feature Let's take an example of 15. You have a mean of your data, so I'll just take a mean, say 10, and then you have the standard deviation of your data, which say is 2. So what you do is you take your feature 15 minus 10, the I'll write that actually, feature minus mu upon sigma, and that is the formula for z-score normalization. So feature minus 10, that is the mu, upon 2, and that would be like literally 5 by 2, and that is 2.5. So that is like z-score normalization. And as do you guys remember, like from the last trimester, like what z-score exactly is? Anyone? Does anyone remember z-score?
We try to find out outliers and
Hmm.
To convert it into standard form, right?
Mm, kind of, yeah, you do convert it into standard form, but what does it tell you? Like a z-score of
How
2.5
far? How far is my data from mean?
from the
like
mean. Yes.
to
How
help
many
the
standard
outliers to finding
deviations?
out outliers.
It is how many standard deviations away are you from your mean. So if this was the mean, sorry, if this was the mean, and this was your data, and this was the standard, say this was the line for standard deviation. So this is 1 sigma, this is 2 sigma, this would be 2.5 sigma, right? And that is the z-score. That is like this thing. So you're basically just like finding out how far the thing is from the mean by in scales of standard deviation. Anyway, so let's do one more method of max absolute normalization. So 3 max absolute normalization, and all you have to do here is like say feature normal. Okay, so feature normal, I'll write it like that, equals to feature upon maximum of that feature, and that in absolute form. So a good example is like, if like your current data is 25, f is 25, and the highest data point in your data is say, um, 50. So let's say max of f equals to 50. That is already in positive, so absolute value will still be in positive. So you just do 25 over 50 and you get the zero point 0.5 normalized data. Very simple. Then there is also decimal scaling. Now this one's like depends on for decimal scaling. This one really depends on like what you want out of your data. So imagine if I had 120,000 and I want to scale this down, I could scale it down to 1.2 or I could scale it down to 0.12. That depends like which one do you want. If you want this one, then good. If you want this one, then yeah, that is also possible. By general definition, what you do is you do 10 to the power I, and then above that you have the number, so the feature. This I is the highest value. Uh, no, I is the lowest value. I is going to be the lowest value. Is the lowest value, which takes your result below 1. So this one, by the way, this is by definition, but you are definitely allowed to do this. So this is decimal scaling. So for example, this one, so 120,000 would be 10 to the power 1, 2, 3, 4, 5 to get 1.2, and 10 to the power 6 to get 0.12. So yeah, that's decimal scaling. There is also robust scaling, fifth method, robust scaling. And in robust scaling, it is kind of more about median rather than like using mean. So factor normalized equals to feature minus the median of x, median of f. There we go. And you just divide it by the interquartile range. of whatever that feature is. I mean, wherever that feature lies, by the way. Ouch, sorry about that. So for this one, I guess the example could be if you have a feature equals to 20, median might be like say 15 or something, and the interquartile range for that, this part is say 10. You just do a division, so 20 minus 15 divided by 10, that would be 5 by 10 equals to 0.5 again. So kind of simple. Again, you're just trying to like fit the data between 0 and 1, by the way. That's all normalization is. You can do it by logarithms as well. By the way, you guys remember something called vector normalization? Anyone remembers that? Vector or L2 normalization. Basically, it is as simple as taking a feature and dividing it by normalized vector of that feature. Now, how do I explain this? Say this one will only work on like if your feature has like if you're taking multiple features as a single feature, yeah, in that case it turns into a vector, and then you can use this technique. So this feature has to be something like, you know, two-part thing, 3,6 or 2,5 or something like that. And then all you do is you take that 3, you square that, plus 6, you square that, you find the square root of that, and that is what this is equal to. If x is equals to this, then you know the L2 normalization would be division by this. Yeah. So how do I? What's 3 square? Like that's 9 plus 6 square. That's 36. What do you get out of this? 45, and then square root. Oh, that would be like so complex. Let's just make it 3 and 4 in that case. We'll make it easier. 3 and 4. That makes it like equals to 25. 16 and 9, yeah, 25, and which would be equals to 5. So all you have to do is 3 comma 5, and you just divide each one by 5. I mean, because you got this. So this would be 3 divided by 5. How much would that be? 0.6. And this was 4, by the way. 3 and 4, comma 0.8. And that is your normalized vector, basically. And then there is also L1 normalization, which is least absolute deviation. And all you have to do is like you just take the vector, you add them together. So again, vector type. So 7th type of normalization, L1. Also called the least absolute deviation. And all you have to do here is if you have a vector 1, 2, 3, you want to normalize it. I mean, this is like taking 3 features together in a single, as a single feature. And so this is the feature. All you have to do is 1 plus 2 plus 3, which is like sum of these 3, which is equals to 6, and you divide this whole thing by 6. So 1, 2, 3, and you divide it by 6. You get 1 by 6 would be 0.17, I think, 0.33, and 0.5. And that is your normalized feature after that. Then there is logarithmic scaling. Wow, I'm getting like logarithmic scaling. My handwriting is getting worse and worse. Sorry about that, but I will be sending this. Simple formula, log x plus 1 for so x normal. Say all you have to do is log x plus 1. Literally, that will scale it down. Nothing like you have to like you really don't have to do anything else other than that. So for example, if you have 99, simple example, x equals to 99, all you do is log 99 plus 1, you get log 100. And because this is like decimal, natural log, that's just going to be 2. And that's like 8 different methods like to do. Let's do one more. Somehow we have 4 minutes left. Now this one's called power transformation. Power transformation. Sorry about that. Give me a second. I'm gonna get some water real quick. In the meantime, if you guys do have any doubts, by the way, I'll be back in like 1 minute. Okay, I'm back. So yeah, I was talking about power transformation. This one's also called the box and Cox. So that's one normalization. Normalization. And all you have to do is like kind of this is something it's not random, but you have to decide on a term called lambda, and this is decided by you. It can be like it's usually a small value, say 1 comma, I mean 1 doesn't make any sense at all, but 2 3 4, no more than that, I guess. Like it rarely goes above that. It is chosen such that the data is more like it becomes more normal. It is chosen in that way, and the formula for that is kind of simple: x to the power lambda minus 1 upon lambda. So for any x you want to normalize, you use this formula. So for example, you can choose something like, say, x is equals to 8, and let's choose this lambda. Lambda is equals to 2. Then you would have 8 square minus 1 upon 2, and that would actually make this kind of big. So 31.5. Yeah, but that makes it kind of big. Doesn't make much sense to do it like with these numbers, at least. But that is just the formula for it. And you have to choose this such that, this kind of grows smaller in that case. Now, there is also one more part of this. Now, I can't remember the formula for that. This box and Cox one also has this one only takes like positive x. So this has to be positive. The other one is called the U-Johnson, and it also takes like negative, positive, and negative values. So positive, negative, that can take any of those. But yeah, these are like most of the normalization methods. Like I don't think the professor would have like taken anything out of this. I mean, would be anything like out of these 9 or 10 methods, like just not possible. These are like literally all the standard normalization methods. So these are like basically you just remember the formula, and then the most useful one is like min max and z-score. These ones are used the most, whenever you're working with this data. Anyway, so any doubts in this, by the way, so far? With that, we have come to like this part, data normalization. We're done with that. So if I scroll all the way up, we've done like pretty much data sets, different paradigms, and data normalization. This is all we have done covered today. So doubts, anyone? Okay, no doubts. Um, do tell me if I'm going too fast, by the way, because I'm like literally just, uh, I don't know, like we have 10 days. So yeah, accordingly, like increasing the speed.
चलेगा सर, no problem.
Okay. So tomorrow we'll do hypothesis evaluation and we see dimensions and distribution. Although
तो
let
यू
me, yeah,
तो आप
yeah.
जो सर ने बुक बताई वो रेफर कर लो या फिर based
Um,
upon your knowledge.
yeah, the primary issue is like I'm referring to this website. Like it's a book. It's a book like website. It was posted like very early in the trimester. So I've gone through that, most of it at least, and like I'm using that knowledge from that book primarily and what I already know. The primary issue being that we do not have a list of topics that sir has taught specifically. So if we knew like what kind of data normalization techniques he has taught, then we could have just covered this in like less time, say with like 4 or 5 data normalization techniques. So yeah, it really depends like on I'm like trying to cover as much as possible from the syllabus, but
हाँ,
yeah.
like ठीक है, I'll try to check with Vanchika, maybe she had some list.
Yeah, if somebody has a
ठीक है,
list of topics, then yeah, we can like go through this even faster.
I'm asking.
Yeah. So tomorrow we'll first start with VC dimensions and distributions, and then we get to hypothesis evaluation. Because VC dimension distribution is like a practical thing that you just learn after doing it once or twice, and then you do the hypothesis evaluation with VC dimensions as well as like in themselves. So yeah, we'll do
Like
that.
सर हम पीपीटी भी देख सकते हैं, सर ने ऑलमोस्ट पीपीटी रीड करी है
ओके,
तो
अपलोड किया हमने.
आप, हाँ वो गूगल क्लासरूम पे लगभग अपलोडेड है सारी.
ओके, मैं चेक कर रहा हूँ एक
एक
सेकंड.
बार, हाँ वो रेफरेंस हो सकता है आपके लिए अगर किसी के पास टॉपिक्स नहीं है तो.
Okay, machine learning. Yeah, I did check like 3 or 4 of these. वो भी मैंने check किए थे lectures. So
हाँ ऐसे ही उन्होंने अपलोड की हुई है लेक्चर 4
हाँ
लेक्चर 3 करके.
हाँ, ये lecture slide तो है यार एक.
तो मोस्टली सर ने पीपीटी रीड करी है.
This is good. Okay, he has
हाँ
also
ये
done this TP and part. Okay,
हाँ
task
हाँ ये
performance and
स्टार्टिंग में हुआ था वीक
okay,
क्लासेस 1 2 3 में.
okay. So I'll cover this part as well. It's like yeah, that's not that like big. It's mostly theory actually. I don't see anything where you can like wait. There is a linear function. That's weighted sum, right? Okay. Yeah, weighted sum. That's okay as well. We'll get to that too. Huh. This is okay. I'll use this then. I guess. Yeah. I'll
तो
stick
एक
to
बार सर
this.
आपको पीपीटी गो थ्रू करनी पड़ेगी,
Yeah.
शायद आइडिया हो जाएगा कि सर ने कितना क्या
Yeah.
करवाया है.
ठीक, तो मैं कल है ना इसको जल्दी से पहले करा दूंगा ये पीपीटी में जो कुछ चीजें हैं दैट इज टीपीई एंड ये वाला इवैल्यूएशन फंक्शन एंड देन वी गेट टू द वीसी डायमेंशन आफ्टर दैट. और कहाँ पीपीटी, ये भी है स्लाइड्स 21 जुलाई. ओह, डिटरमिनिस्टिक एंड प्रोबेबिलिस्टिक सिस्टम्स. ओके गुड. वीसी डायमेंशन एंड डिस्ट्रीब्यूशन. हाँ, तो ये वाली
सही
स्लाइड.
करवाया सर.
एक सेकंड, लीनियर रिग्रेशन डेटा नॉर्मलाइजेशन इसमें है. हाँ, linear regression, linear bias, optimal estimation noise. Okay, wow. Okay, so linear model for two data points given by mapping ये data linear model for ये ठीक है, data ऐसे ये दिया हुआ ठीक है. normalization वेट सकते हैं, normalize to range, ये min max वाला है. This is literally the same thing, min max. ओके यार, ये तो एक ही टेक्निक है इसमें. हाँ ठीक है ना, तो मैं जस्ट रिमेंबर मिन मैक्स वाला जो पहला वाला किया था ना, जस्ट रिमेंबर दैट वन, वही बस है.
ठीक है, कोई नहीं, नॉलेज हो गई सर, अच्छा ही है।
ठीक, तो I'll refer to this from like
हाँ
exactly.
सर, यही करना पड़ेगा।
हाँ, हाँ, ओके। चलो, तो है ना, कल क्लास में आई विल लाइक स्टार्ट विद द फर्स्ट स्लाइड का जो छोटा सा रह गया है, दो पार्ट, फंक्शन वैल्यू, सॉरी, वैल्यूएशन फंक्शन एंड दैट अदर पार्ट टीपीई,
ठीक है
वो कर
सर।
लेते हैं, है ना। तो आज की क्लास यहीं पे ख़त्म, 1 घंटा तो हो ही गया। आई थिंक प्रसन्ना हैज़ रिकॉर्डेड इट, so let's do it, like let's continue tomorrow. And by the way, you guys, if you have like anything you want to personally like have like any discussion thing in this subject, so we can